Okay, so we are finally at the third session, which is also the last one for tonight event, the next research line fair event, Heterogeneous High Performance Computing, which is going to be presented and chaired by Guido Walter Di Donato. He's also a postdoc in the next lab. So please join me in welcoming Guido Walter.
All right. Thank you, Marco, for the introduction. And so let's start with this last session, Heterogeneous High Performance Computing at NextLab. So this will be a rapid overview of this research line. So to start, let me just introduce myself again. I'm Guido Walter Di Donato. I'm a postdoctoral researcher here at NextLab. I got my Bachelor and Master of Science in Bioengineering and Biomedical Engineering from Politecnico di Milano and UIC, and my PhD in Information Technology in the area of Computer Science and Engineering here at Politecnico. My interests mainly are around high-performance computing applied to graph analytics and graph machine learning, and bioinformatics and health informatics. And if you followed the first section, you probably already know that I'm also interested in entrepreneurship, and I'm the CEO of Genogra. So in this talk, I will provide a rapid overview of our research line about heterogeneous high-performance computing. And we start from the context that is the need for more efficient architecture. So in this research line, we are focusing on some compute-intensive algorithms and computations that require to process a massive amount of data. And for this kind of computations, general purpose architectures are already proven inefficient to do this massive work. So hardware accelerators like GPU and FPGA offer way better performance to speed up this kind of processes. But in this research line, recently, we have also started to explore another direction to speed up this kind of programs. And this is the case of quantum computing that we will explore later. So we are also trying to radically change the paradigm of the analysis and of the computation to get some outstanding results in terms of performances. So moving to what is the high-performance, heterogeneous high-performance computing at NextLab, we have mainly two kinds of directions. The first one is using GPU and FPGA to speed up some of the processes. The other direction is using instead quantum algorithms and quantum computers. So moving to the first kind of works that we do at NextLab, let's start with GRCUDA. GRCUDA is an example of what we do to, let's say, make GPU computation more accessible. So GRCUDA is basically a polyglot API that gives CUDA to every programming language, high-level programming language available in the Graal VM by Oracle. So this project was initially created by Oracle and NVIDIA, is currently maintained by us, and we gifted GRCUDA of an asynchronous scheduler both for single GPU, but more importantly for multi-GPU. We achieved multi-GPU scheduling in an automatic way by minimizing the data transfer and maximizing the GPU utilization through some policies that take decision on how and where to schedule the kernel execution at runtime. This project was very important for us, and we achieved an automatically achieved a performance of 80–90% with respect to the CUDA C++ peak performance with respect to manually optimized implementation. So these are very remarkable results. And for this reason, we asked ourselves, can we do the same in a distributed scenario? So can we do this autonomous scheduling on multiple accelerators in a distributed scenario? And this is what the talk by Jan that will follow and that will present GR out will be about. Another kind of work that we do in our lab is to accelerate some heavy computations. In particular, one of our field of application is that of graph analytics. In this case, we know that these huge graphs can be analyzed very rapidly by using them in form of matrices and using some hardware accelerators. And this is exactly the kind of work that we do in our lab. An example will be provided by Mauro Famà that will present a multi-GPU top-K sparse eigensolver for graph analytics. We also used GPU and FPGA to accelerate genomic computation. This is mainly the work by Alberto and Beatrice. They achieved some huge speed up by using this kind of architecture. And in particular, with the work by Alberto, he tried to understand if in a certain way he could generalize the optimization process. And this will be the topic of the Starlight talk that Alberto will present after. Finally, to conclude this overview, this very rapid overview of our work, let's mention the final kind of work about the quantum computers. These are new way of achieving some exponential speedups for certain kind of algorithms. This is an entirely new paradigm of computation that is based on quantum mechanics. So we are not using any more bits, just 0 or 1s, but we are using qubits that can have as values some superpositions of 0s and 1s. So the output of this algorithm is generally probabilistic, and they are great, for example, for some specific kind of computation like combinatorial optimization. But this kind of computations comes with many open challenges. In particular, for example, the topic of the talk by Marco Venere will be about the need of mitigation, of error mitigation, for example, in combinatorial algorithms. So this is mainly the overview of our work in the HHPC research line. Thank you for your attention. And now I will leave the stage to the next talk, that is Jan Di Dio Lavora. So, Jan, the stage is yours.
Thank you, Guido, for the introduction. Hello, everyone. My name is Jan, and today we are going to talk about Jira Out, a way to distribute your workload in an agnostic manner. But first, a little bit about myself. I'm a second-year PhD student in information technology. I manage the partnership between Oracle Labs and NextLab, and I am an HPC intern at the Pacific Northwest National Laboratory. My main interest revolves around high-performance computing, distributed system, and cloud computing. But let's switch to the topic of today, GPUs. We have all seen how GPUs have been adopted in a wide range of scenarios and in top 500 supercomputers. The workloads are such as genome analysis, weather forecasting, graph analytics, and molecular dynamics. But in the past few months, we have all seen how GPUs have become the de facto standard for accelerating the training of large language models. Also, cloud providers have found in GPUs a great opportunity, and they're now offering on-demand access to GPU and multi-GPU architectures to the end user. Unfortunately, the required expertise to fully exploit those hardware accelerators is still high, and in novel emerging domains, this is a problem. Multiple hardware vendors have tried to simplify the way with which users can accelerate their application with a GPU accelerator. One of those is the unified virtual memory. That is NVIDIA and also other cloud providers provide unified virtual memory. It's a way to give the user a unified address space among the different hardware accelerators that are available on the system, avoiding a manual memory management, needing for implementing batching mechanism, and overall providing the access to what is called the unified virtual memory oversubscription. That is the ability to access memory regions that are bigger than the on-device's memory one. And therefore, it provides a simple programming paradigm. But there is a problem with that. Let's see a case study, the Black-Scholes benchmark. This is a benchmark that forecasts the future stock prices in the European market, and it is a very massively parallel workload. On the right, you can see the execution times on two NVIDIA server-grade GPUs, the V100, with 16 gigabytes of memory and 32 gigabytes in total. This benchmark is massively parallel, so there are no intricate interdependencies between the different kernels. And as you can see, there is a massive performance degradation by switching from the 32 gigabytes to the 64. We are not going to doubling the execution times, but we are going to hundreds of times more. And the difference is the fact that you are switching from the 32 gigabytes to the 64, actually enabling the GPU over subscription mechanism of unified virtual memory. That is the ability to access more memory inside of our hardware accelerators. How can we solve this problem? We can either choose to hand-tune the unified virtual memory by using the CUDA memprefetch and CUDA advice that are utilities that CUDA offers to the end developer, but you need to match the black box model of the unified virtual memory behavior since it is a proprietary technology. And moreover, the hand tuning that you are doing is workload specific and it requires multiple trial and error cycles. And finally, there is a high expertise required to perform all of those operations. The other way is to scale out your application to actively reduce the oversubscription of each hardware accelerator. There are multiple frameworks that allow you to do that, such as CUDA-Aware MPI, Nickel, or NVSHMEM. But they require you to restructure completely your workload and to adopt predefined programming paradigm. Therefore, the high engineering effort combined with the high expertise required does not offer a great solution in scaling out. But what if there was another option? And GROut is that other option. GROut provides a way to transparently scale your workload, access scaling into multiple programming languages thanks to the GraalVM backend with JavaScript, Python, or Java, and requires minimal expertise thanks to the simple APIs of the framework. Here's an example of an application written with GROut. You just have to import the polyglot capabilities of GROut into your application, and then you can access capabilities such as runtime completion of CUDA kernels, and you can either compile them at runtime, or you can bind precompiled kernels or libraries to your application. You then have to create a space and some memory managed by GROut, and finally the user can adopt its normal workflow for accelerating its application without having to worry about distributing the different kernels. In this example, there is just one kernel. But if there are multiple kernels, the GROut APIs will take care of everything for the user. The architecture of GROut revolves around the creation of a computational element. That is a wrapper around the function calls that access GPU memory, for example, launching kernels or access to GPU accelerated libraries. And this provides the polyglot interface of GROut. Then we have the second component, which is the controller. The controller uses these computational elements and takes care of and understanding the dependencies between the different computational elements. And its final goal is to schedule a precise computational element into one of the nodes available in the system, effectively doing an inter-node scheduling procedure with multiple scheduling policies. On the lower level, we have the worker. The worker instead provides an intra-node scheduling procedure that is optimizing the placement of the computational element inside of the single node to actually exploit all the different hardware accelerators that are available in the system. We tested our architecture into three different benchmarks, and on the right side, you can see with the round slots, the different computational elements that are inside of the different benchmarks, such as the machine learning ensemble, where we have an unbalanced branch, where we have a branch that takes more time to execute, and another one which is shorter. On the conjugate gradient, we have instead complex interdependencies between the different computational elements. And finally, on the matrix vector product is an example of a massively parallel workload. So the first question that we try to answer is, are those workloads that are publicly available also affected by unified virtual memory slowdowns as the Black and Scholes one? The answer is yes. They are indeed affected after reaching a predefined oversubscription level, such as switching from 32 gigabytes to 64 or from 64 to 94 gigabytes. An exemplary example is the matrix vector multiplication, where switching from 64 to 96 gigabytes reaches the out of time that we define for the overall benchmarks that is greater than 2.5 hours. So is scaling out with GROut just by going adding one more node to our architecture a solution to those problems? Indeed,
Jan, I think we cannot hear you anymore. Jan? I'm sorry, I think Jan audios is completely disconnected because he cannot hear us anymore. So, okay, I think that due to this technical problem, we can start and we can move to the next talk. So, sorry. Okay, Jan is not hearing anymore. So, okay, let's move to the next talk. So please, let's leave the share. Let's leave the stage to Mauro Fama. Jan, please. Yeah, I cannot kick him out. Okay.
Can I start?
Sorry, just a moment. These are the technical problems that, of course. Okay, so. Mauro, try to present your screen. Okay, so sorry again for this technical problem, for the interruption of Jan talk. Let's move to the next talk, that is the design of a multi-GPU top K eigensolver by Mauro Fama. Mauro, the stage is yours. Okay, so we have a technical problem also with Mauro. Basically, we cannot hear anybody presenting from remote. So
maybe now you can hear me.
Okay, Mauro, maybe you were just muted. Okay, so please start again from the beginning.
Okay.
Thank you.
I'm Mauro Fama. I'm a computer science and engineering master student at Politecnico di Milano. And I'm here to present you my project about the design of a multi-GPU top K eigensolver. The goal of this project is to develop an algorithm that is capable of extracting the largest eigenvalues and eigenvectors of large-scale sparse matrices. The solution that I designed takes advantage of GPU acceleration and handles very large datasets. The development environment that I used was CUDA on C++, which allowed me to create an application capable of running on NVIDIA GPUs. Eigensolvers are algorithms used in engineering disciplines to solve analysis, design, and optimization problems. These functions are a fundamental concept in linear algebra and have plenty of applications in a variety of fields, enabling understanding of fundamental properties of a variety of complex systems. However, eigensolvers are computationally intensive algorithms. and they involve computations on large and often sparse matrices. GPUs are particularly well suited for accelerating these computations, primarily because they are designed to perform parallel mathematical operations on thousands of cores. This makes them extremely efficient at processing large amounts of data, which is essential for eigensolvers, which involve matrix operations on many units of data simultaneously. GPUs have high bandwidth memory, which can be used to store large matrices and the intermediate data between the computations. All of this makes GPUs a very advantageous option for performing eigensolvers on large datasets, significantly reducing the computation time and enabling analysis of larger, more complex problems. The Lanczos algorithm is a numerical method that is used to compute the eigenvalues and eigenvectors of a matrix. This method is mainly used for large and sparse matrices, and is particularly efficient for finding some of the largest or the smallest eigenvalues. The algorithm, in addition to taking as input the sparse matrix, will also take in input the desired number of eigenvalues, k, and a vector v that is initialized with all values to 1 divided by the number of rows of the matrix squared. The algorithm extracts parameters from the matrix that we call alpha and beta. They will compose a three-diagonal matrix that will have the same eigenvalues and eigenvectors as the original matrix, but will have a dimension k per k, much smaller than the input matrix of dimension n per n. K is in the order of tens, while n could be in the order of tens of millions. The Lanczos algorithm is an iterative algorithm. The same procedure is repeated k times. That is the number of eigenvalues that we want to extract from the matrix. A series of computations are carried out on the input matrix. Sparse matrix vector, scalar product, linear combination, and normalizations. From the resulting vectors of these operations, we are able to extract two significant values that we call alpha and beta at each iteration. They will compose the resulting three-diagonal matrix that the Lanczos algorithm returns. The iterations will be mutually dependent. It means that the input vector of each iteration will be obtained from the previous one. To extract the eigenvalues from the small tridiagonal matrix, which correspond to those in the original matrix, we use Jacobi's algorithm. The algorithm iteratively applies rotations to the matrix until it becomes approximately diagonal, and the eigenvalues can be found right in the diagonal. Jacobi's algorithm is relatively simple and can be used for small or medium-sized matrices. It is not the most efficient method for a large matrix because of its iterative nature and the need for many rotations. This step is computationally much lighter than Lanczos, such that it will fail to saturate the memory of a single stream of a modern GPU. So we perform it CPU side, not going to affect the overall performance of the eigensolver. One problem to be handled in the Lanczos algorithm is the rounding of the floating points. We are going to process very small data, and as the iteration progresses, the truncation could lead to Lanczos vectors no longer being orthogonal to each other. To measure this property, we perform the scalar product between all combinations of Lanczos vectors. It will return the degree of orthogonality between the two vectors, which should be as close as 0 as possible. A widespread and already approved state-of-the-art technique is partial orthogonalization. It involves orthogonalizing vectors during the iteration of the algorithm. This can be done by performing a scalar product and a subtraction between vectors, which in this case involves Lanczos vectors. Performing this step every 2 iterations is the right trade-off, since it does not excessively increase execution time, but guarantees orthogonal vectors to within a couple of degrees at the end of the entire process. Regarding the implementation of the algorithm, the computations are mostly dependent on each other. Each one needs the output of the previous one to continue. As a result, the parallelization strategy of this algorithm is data-oriented. The operations that we perform on the matrix can be performed simultaneously on smaller portion of the matrix, and then we can reaggregate the partial results. So the strategy lies in performing the same computation in parallel on different partitions of the matrix. If you have two devices in our system, the matrix will be partitioned in such a way that non-zeros will be divided as equal as possible between the two GPUs. So the same kernel will run in parallel on two different devices and with a smaller portion of data, resulting in a decrease of execution time. The partitioning policy is made to scale as the number of GPUs in the system increases, making sure that the portions are as balanced as possible. The input matrix is given in input using the coordinate list. That is an efficient data structure for sparse matrices. And the partitioning algorithm divides the matrix by columns. The algorithm, when partitioning the matrix, does not allow a column to be broken in two, avoiding it going into two different partitions. It is designed in this way to not cause any correctness problem. To test the algorithm, the sparse matrices were taken from a collection released by the University of Florida, sparse, and they represent topologies of graphs used in various domains of engineering. However, the eigensolver is agnostic to a type of data represented by the matrix. The environment in which we launched our test consists of 8 NVIDIA Tesla V100, each with a capacity of 16 gigabytes. We measured the execution time using 1, 2, 4, and 8 GPUs, studying different behaviors with very different amounts of available memory. To compare results, we used as a baseline to calculate the speedup the RPAC library that is available for CPUs, which is then compared with the speedup obtained on the same library, but from the current best performing state-of-the-art implementation. The indicators that we used refer to both execution performance and eigensolver accuracy, trying to measure the overall quality of the algorithm. An important evaluation was made with respect to the execution time. The results are compared first with a standard library for solving mathematical problems of this type, which is RPAC. And it is immediately noticeable that GPUs are a much better hardware for solving these kind of problems. Both implementations that take advantage of its acceleration bring a very significant speed up on all the matrices used for testing. The two speed ups we compare are of the current best performing state-of-the-art implementation, and in this implementation that takes advantage of the power and flexibility of CUDA. With my implementation, memory is manually handled, as well as scheduling and kernel synchronization. A minor but still very significant speed up is seen for the 50 plus gigabyte matrices, cron and urand. For this, the kernel execution times are really high, and this becomes a bottleneck even with high optimization. Regarding the scalability of the algorithm, for very small matrices, the one in the lowest part of the graph, we are talking about matrices that do not reach the gigabyte of size. It is very difficult to saturate the streams of the powerful GPUs that we used. And also because of the GPU to GPU and inter-GPU transfers, as the number of devices increases, the data transfer becomes a bottleneck, resulting in a faster execution using only one GPU. A very different case is that of the matrices that completely saturate the GPU memory, like cron. In this case, we can see how distributing the workload results in a significant decrease in execution time as the number of GPUs increases. We do not have an additional speed up on 8 GPUs since in the architecture we used to test, not all the GPUs are connected with the fast NVLink. So making a transfer via PCI becomes mandatory, and the problem is that the transfer rate is about 10 times slower, creating a significant bottleneck. Regarding the evaluation of the quality of the eigensolver, one important metric is definitely the degree of orthogonalization of the Langsos vector, that by definition, they must be orthogonal. We cannot guarantee 90 degrees orthogonality, but thanks to the partial orthogonalization, as the eigenvalues we want to find increase, we reduce the distance from the ideal 90 degrees. From this graph, in which we also report the results without the orthogonalization, we notice how it is a key step because of the truncation errors. In conclusion, the goal of this project was to design and implement a program that is capable of extracting the largest k eigenvalues from a very large-scale sparse matrix. We were able to achieve performance comparable to the state of the art while demonstrating the quality of our eigensolver. One work being planned is to optimize the use of unified memory. CUDA provides several functions that allow us to give hints to the compiler on when to make the transfer between CPU and GPU to prevent page fault from occurring, which, despite being handled, slows down the speed of the execution in certain cases. In addition, since the algorithm scales differently depending on the size of the input matrix, we would like to implement a policy that adjusts partitioning dynamically based on the number of GPUs available in the system. So that's all for my presentation. Thank you for the attention.
Right. Thank you, Mauro. So I have a question for you. So basically, you talked about sparse matrices as input of your program, of your implementation. It is also possible to apply your solution also to dense matrices or just on sparse matrices? And if you tested many levels of sparsity in the matrix, which kind of, let's say, levels did you test? So how many non-zero elements that were present in the matrix?
It is possible to use it for dense matrices, but the fact is that it will not be efficient. The only constraint for the input matrix is that it will be Hermitian. It needs to be an adjacency matrix, a symmetric matrix. So the problem is that the algorithmic time complexity of this algorithm is dependent on the average number of non-zeros on the rows. So if the matrix is not sparse, it will not be efficient as it is for sparse matrices. About the testing, we use the real-world use cases. So with sparse matrices with from 1% to 4% average non-zero values, but we see that as the number of non-zeros increase, the execution time increases as well.
All right. Thank you again for your talk and your answer. So if there are no any more questions from the chat, I will leave the stage to our next speaker, Marco Venere, that will talk about error mitigation techniques.
Hi, everybody. Let me share my screen. So thank you, Guido, for your introduction. I'm Marco Venere, and today I will talk about quantum error mitigation applied to a QAOA workflow. In particular, this project has been made in collaboration with the Quantum Open Source Foundation. But let's start from who I am. I'm a PhD student at the first year in information technology here at Politecnico di Milano. And concurrently, I'm also a research intern in AMD and have been a student member at the Quantum Open Source Foundation. My main research interests are related to quantum computing with quantum error correction and mitigation, and computation on quantum circuits and their optimization, high-performance computing with the design of advanced heterogeneous architectures, and other design with FPGAs. And today, we will talk about quantum computers. They exploit laws of quantum mechanics to achieve a super polynomial speedup with respect to classical computation. In particular, the unit of information is the qubit, which may stay in two possible states at the same time, thanks to the superposition principle. This principle, together with other effects like entanglement, allows us to get exponential speedups in a lot of interesting use cases. And today, I will talk about one of these use cases, which is combinatorial optimization. In particular, I'm referring to an algorithm called quantum approximate optimization algorithm, in brief QAOA, which solves combinatorial optimization problems. it receives an input problem with this following formalism, where you have an objective function f of x that you want to minimize, subject to some very specific constraints. Starting from this formalism, we define a quantum circuit, which is called in jargon ansatz. It describes all the possible operations to perform on the qubits. As you may notice, this circuit is parametric. Indeed, it must deal with betas and gammas parameters that must be tuned in order for the circuit to give as output the correct solution to the problem. To perform such a tuning, we use an optimizer. State-of-the-art has a number of possible optimizers to consider, and in this work, we are considering in particular Kobila, Powell, Nelder-Mead, and fake nodes. Well, this process seems easy, but telling the truth, it's really not. Indeed, quantum computers must deal with noise. Here you can see a graph representing the quantum processing unit of a well-known quantum computer, which is the IBM Q16 Melbourne, and its physical constraints. In particular, all the nodes represent qubit, and as you notice, there are numbers associated with these nodes. Indeed, they represent the error rates for operation applied on a 1 qubit, and also the readout of its value. In addition, we can see on the edges other numbers which represent error rates for a 2-qubit operations applied to a specific pair of qubits. These errors deteriorate the final quality of the output of the algorithm in such a way that QAOA becomes not practical at all. Therefore, the research objectives of this work are firstly to mitigate the effects of noise, in particular using some state-of-the-art techniques for error mitigation. Also, we want to perform an effectiveness analysis of this approach to see if it is really functional for two well-known optimization problems, which are the maximum cut problem and the knapsack problem. Let's start with the first point. One of the most important mitigation technique is the zero noise extrapolation. Let's imagine that we have a circuit that we want to mitigate. And in particular, looking at this circuit, let's focus on these gates. These are the quantum equivalents of the negation belonging to digital circuits, like the NOT operator. And as everybody knows, two negations cancel out. So what we can do in this circuit is we can add pairs of these negations. And as you may imagine, the final output of the circuit is just the same as the first one because they are functionally equivalent. The difference is just that the circuit is longer. We can keep on replicating these gates and producing several different circuits, each one being longer and longer than the previous one. All of them are functionally equivalent, but this difference in the depth of the circuit implies that they are more and more affected by noise. What we can do then is we can measure out these circuits. And since their output is probabilistic, we compute the expectation value of their output. And we plot it. As you can notice, here we have the expectation values as the length of the circuit increases, and so as the noise intensity increases as well. In this way, we can extrapolate what happens when zero noise is applied to the circuit. This extrapolation will produce the mitigated expectation value. That will be the correct output of the quantum circuit. Well, we introduced this technique into QAOA, and in particular, we modified the optimization step. Indeed, the optimizer will not receive as input the generic original quantum circuit, the ansatz, but its modified version after applying the mitigation technique. We are using, in a technical sense, OpenQAOA, which is a state-of-the-art framework to run QAOA problems, and MITIC as a state-of-the-art library to perform zero noise extrapolation. Now that we have seen the integration process, let's focus on the effectiveness analysis to see how the optimizer behaves as we apply this integration. We'll consider, as I told you before, the maximum cut problem and the knapsack problem. And since OpenQAOA and MITIC are frameworks that both have several parameters, we perform an exploration of the parameter space in order to find out the effects of our work. Let's start with the instance of a maximum cut problem. Here you can see the same instance given as input to do two different optimizers, Kobila and Powell, in a noiseless case. As you can notice, Kobila only requires 200 iterations to reach the solution to the problem, while Powell requires more than 3,000. While their solutions are comparable, the execution time required by Kobila is significantly reduced with respect to Powell. So we will pick this option for our study. And we apply noise. As you can see, the performance of Kobila after applying noise are way different. Even though the general trend of the exploration of the space is quite similar, the final values of the objective function are way higher. And since we are doing a minimization problem, this means that the final quality of the output is lower and reduced. So what we need to do in this case is to apply zero noise extrapolation. Let's test two different extrapolations techniques shown here in green. On the left side, you can see the exponential extrapolator working on. And as you can notice, even though it initially overlaps with the noisy trend of OpenQoA, in the very end, it reaches a lower solution. This means that the mitigation technique is actually working. On the other side, the linear extrapolator completely overlaps with respect to the trend given by the noisy case. This means that we are not reaching any valuable effect thanks to this method. Let's now move on to another case with the knapsack problem. After doing the extensive exploration of the parameter space, we found that Kobila is the best solver. We apply noise, and we see what happens when the zero noise extrapolator is performed by using the exponential extrapolator and the fake nodes extrapolation. As you can see, the exponential extrapolator does not really follow the trends of OpenQoA. Indeed, after modifying the parameters, the optimizer gets stuck in a local minimum, which is way less efficient than the local minimum found by the noisy OpenQoA. This means that even though we are technically mitigating the effects of noise, we are altering the exploration of the parameter space in such a way that we cannot really go to the correct solution to the problem, but just to a local minimum, which is very inconvenient. On the other side, the fake nodes extrapolator completely overlaps with the noisy case. As a final conclusion, we can consider the effects of zero noise extrapolation as very case-dependent. They are really based on the specific instance of the problem, and we cannot really generalize. Even though there are cases where the effects of zero noise extrapolations are meaningful, there are other cases in which they are disruptive, and they really make us very farther from the correct solution to the problem. In conclusion, we tested the integration of zero noise extrapolation in a QoA framework, and we also evaluated the effectiveness of this approach with respect to two well-known optimization problems. And as next steps, we want to consider a further mitigation technique, which is the probabilistic error cancellation. Also, we want to evaluate the effects on another very important optimization problem, which is the aircraft loading optimization. Finally, we want to test the same framework on multiple quantum processing units. Also, I would like to talk about my future research direction. In particular, I will work on a focus on a workflow for the compilation of quantum circuit, and in particular, we consider the optimization of the circuit and the mitigation of the error by viewing also multiple QPUs. And I will even consider advanced heterogeneous architectures that will involve the quantum processing units to get further acceleration and speed up. I'm also available here for any research internships and visiting periods. With this, I thank you all for your attention, and I'm here available for any question.
Thank you, Marco, for your talk. I have a question. You talk about error mitigation techniques, but we know that in the quantum world, there are also error correction techniques. So
yes,
can also error correction techniques be applied to QA/OA workflow, or just error mitigation? And if you can briefly explain the difference between the two techniques.
Yes, thank you for your question. It's very interesting. Indeed, they can be applied to a QAOA workflow. In the error mitigation case, what we are doing is we are using statistics and probability to try and figure out what is the correct output of a quantum circuit. While in the error correction case, we exploit some ancilla qubits that are inside the QPU, we measure them, and we try to understand the specific errors that have occurred inside the algorithm. And to do so, we want to undo the effect of noise. There are some possible algorithms to do so, like the minimum weight perfect matching or the union find, which are decoding algorithms, because given the measurement of these qubits, they can decode it and provide a correct solution to the problem by undoing the effects of noise. And they're mainly performed on FPGAs. And here in Next Lab, we are also focusing on the acceleration of decoding algorithms in order to enable further and further quantum engineers to make the usage of quantum computers even more practical.
Okay, thank you, Marco.
Thank
So
you.
if there are no more questions in the chat, I will leave the stage to our last speaker for this session and also for the whole event, Alberto Zeni, that will talk about Starlight, kernel optimizer. So let's try to open these slides. All right. So the stage is yours, Alberto.
Thank you, Guido, for the introduction. So hi, everyone. My name is Alberto, and today I'm going to present you Starlight, which is a kernel optimizer for GPU processing. But first, I would like to briefly introduce myself. So I'm a postdoc here at Next Lab at Politecnico di Milano, and my research focuses on HPC. Sorry, I think that we have an issue with we are not sharing the screen. Let me start again. Okay. Okay, so let me just check. Okay, so again, I think that I can skip this slide. So I was briefly introducing myself. So my name is Alberto. I'm a postdoc here at Next Lab at Politecnico di Milano, and my research focuses on HPC and genomics. So pretty much HPC applications and hardware accelerators on the genome analysis field. And in this regard, as previously introduced by both Eleonora and Guido, my work is on trying to go beyond the capabilities of current general purpose processors, because the applications that we focus on genome analysis are particularly computing intensive and also required to analyze a lot of data in order to be effective to the end user. So in order to go past the limitations of general purpose architectures such as CPUs, which right now are currently going against the limitations of physics for what was dictated by Moore's law, I'm targeting GPUs and FPGAs as hardware accelerators for genome analysis. And in particular, as we already saw in the previous presentations, during my PhD, I developed multiple solutions which enable significant performance and energy efficiency improvement with respect to state-of-the-art solutions. And also, I have been able to deploy these solutions into state-of-the-art tools in order to make them usable and useful for other researchers that might be leveraging these particular applications for their analysis. But during the course of this, I stumbled upon the fact that I needed a way to develop applications in an organized manner and in a standardized manner. So I wanted to develop something that was able to help me and help other researchers to develop high-performance applications, and not only, of course, targeting genomic applications, but also other applications that were leveraging hardware accelerators. So on this, I started developing a tool which targets specifically GPU kernels, which provided in-depth performance analysis and correlations of bottlenecks with respect to the code lines that we have development of the compiled code, and also suggestions based both on the low-level performance of the based on the performance of the code, and also based on the roofline model principles. So this became Starlight, which has a lot of benefits and a lot of capabilities with respect to developing high-performance kernels for GPU. First thing first, we enable the definition and the generation of a roofline model automatically for any CUDA-capable GPU. We also have the possibility of analyzing kernel stalls and highlighting the various parts of the code that cause the most issues. And also, we are able to not only highlight the issues, but also provide some insights on how the users can apply particular optimization that we suggest in order to solve these issues. Provide also a projection of the possible performance improvements by resolving these issues. And also Starlight is the first tool that has the possibility of drawing and of generating, analyzing all the native data types for all the native data types, and also automatically deploying and describing multiple memory hierarchies on the GPU side. And sorry, I went ahead a little bit. So this is a quick overview of Starlight. Starlight has three main parts. The framework of Starlight describes a framework which has three main parts. The first one is the roofline generator, which describes and takes the information regarding the current GPU that you are targeting and describes the roofline model. Then we have a performance analyzer, which leverages CUDA and NVIDIA CUPTI to take information regarding the performance and highlights hotspots. And then we have an optimization parser, which takes the information of the two previous modules, so the roofline generator and the performance analyzer, and correlates them in order to provide accurate suggestions for the end user in order to optimize their code and so on and so forth. So, of course, Starlight is intended to be used in a cyclic manner. So the code should run through Starlight multiple times, but also can be used, for example, to only draw the roofline model if we are on a page. So if you want to only look and have a high-level overview of what your kernel, how your kernel is doing on your GPU, you can just do that. So as said, one of the first step and one of the key elements of Starlight is the roofline model, which is a very useful and very immediate way on a way of observing the performance of your application on the particular architecture that you are deploying it. And it gives you, if you know, pretty much an overview, a visual intuitive method, a method to portray the performance with respect to the limitations of your architecture. So with respect to the memory bandwidth of your architecture and your peak performance that you can achieve. So the first step, as said, of Starlight correlates to this. So we have an automatic hardware detection kernel that pings the GPU and draws the analytic or the theoretical performance bottlenecks on the GPU, as you can see on the right. So on the right, we have a definition of the roofline model, and we can see that we draw multiple levels of cache, and also the peak GPU performance. We can do this analytically, so by pinging the GPU and retrieving some information regarding the number of cores and the frequency of how the stuff is working, or also we can apply and we provide optional micro benchmarking. So if we want to have a better level of detail with respect to the performance that we can achieve, we also accept that information. So in order to draw a better, a more accurate description of your architecture. So this is the first step for the roofline generator. Then we move on having a first performance analysis, exploiting either NVIDIA NVProf or NVIDIA Insight, depending on the generation of the GPU that you are currently targeting, and pretty much extract the performance of your kernel and plot it on the roofline model. To do all of this, we use Python mainly for scripting and Matplotlib to plot everything on a graph. So the next step is, of course, the performance analyzer. So first, we exploit the CUDA-CUT API in order to sample the application and to have a better understanding of the performance. So we execute the application a bunch of times and extract all the possible information that we could in order to better draw our conclusions of where the bottlenecks are. And then we correlate this information with the SaaS low-level assembly, which gives us a bunch of information regarding the symbols, the code sections of the compiled code. And so that we can basically, in this way, highlight the hot spots of the code and correlate them with a specific code line. Finally, we have the optimization parser, which takes all the information of the two previous models and regarding the stalls, the kernel structure, and so on and so forth. And depending on the nature of the stall and on the kernel performance, provides a suggestion on how to optimize the particular part of the kernel and how to solve the issues that we might see with the respective code line. So this is a quick overview of what we can see of a kernel. So let's say that we have this particular kernel that is performing very poorly. Is in the kernel performance right now. It's in the memory bound zone, but it's not touching any of the lines of the roofline. So the first thing that we might suggest is, for example, trying to solve some issues regarding the dependency, and then moving on, trying to solve more issues by increasing the resource utilization. And then maybe we can reach a point where we have a high enough performance that we are reaching the one of the lines of the roofline. So that here we have, for example, by solving some thread synchronization issues, we might be able to touch the roofline at that point. And so we want to move to the compute bound part of the roofline. And in order to do so, we introduce some memory optimization. So we increase the memory usage and the shared memory usage and use higher memory available on the GPU. And finally, we might have some ways to improve the number of operations per byte that we perform. And so we can finally, if all goes to plan, at the end, reach the peak performance of our GPU. So in order to prove that Starlight actually works, we tested it on 3 different applications. Here I'm going to be describing 2. So one is an application for genome analysis. As said, this is from my background, from the background of my PhD. And this is already optimized and state-of-the-art application that we just took from the original GitHub repository and tried to optimize further. And then we also exploited Starlight to, from the ground up, develop a new application for image registration. And with respect to the various architecture that we tested, of course, Starlight, one of the key features of Starlight is the fact that it can work with older and newer GPUs. And we tested all of this on multiple architectures using multiple GPUs, both from the mobile and desktop and data center side, on multiple generations of NVIDIA, using multiple generations of NVIDIA GPUs. So with respect to Logan, so the genome analysis kernel, we saw an improvement in performance of over 2.5 times. This is with respect to the best performing kernel. But as we can see here, we observe an improvement at least relatively of 40% with respect to the original implementation when the kernel was optimized by Starlight. And when moving on to the mutual information for image registration kernel, we observed that we were able to deploy and develop an application that was running 12.7 times faster with respect to the state-of-the-art application deployed on FPGA. So in this case, we observed multiple performance improvements, as we can see here. And pretty much this proves that Starlight is not only applicable to a singular application, but also it is applicable on multiple architectures and multiple and a broad set of applications. So you are free to test it out. The code is available online. And as said, this was pretty much the end of my presentation. So we showcased Starlight and how we can improve both the performance of already optimized kernels and how it can help you to develop new kernels. And I detailed all of the characteristics of Starlight, which can help you not only to optimize stuff, but also to showcase the performance of your application with respect to your architecture. So thank you everyone for listening to my talk. And if you have any questions, please feel free to ask.
Okay, thank you, Alberto. So I have just a curiosity. You talked about CUDA-enabled GPUs, so I think NVIDIA GPUs. I was wondering if Starlight can run also on other GPUs like AMD, which is the work that you need to do if you want to run on AMD GPUs.
So thank you, Guido, for your question. Yeah, so one of the future works is, of course, adapting Starlight to multiple architectures. So now we started Starlight with NVIDIA GPUs in mind, mostly because they are much more broadly available, but also because the other APIs or benchmark tools for the other GPUs were in a very early stage of development, or for example, in the state of Intel GPUs, they were not particularly broadly available and not even used. But right now, one of the next steps is definitely going to be integrating AMD GPUs first thing first, because AMD is moving towards a more a very, very open approach to their code and their infrastructure, and also because of the rise of ROCm and HIP, which are significantly opening the fact that AMD GPUs can be used for scientific computing.
Okay, thank you, Alberto. So at this point, I would like just to conclude this last session, leaving the stage to Marco for some conclusions.
Thank you, Guido. Thank you to all these speakers, this session chair. It has been a long night, a long day for us. That lasted more than 4 hours and a half. So I do really want to thank all the speakers. We went through 14 talks, 3 sessions. It was a long but very super exciting event. I hope you enjoy it online, and all the videos and the recording and the slides is going to be available online in a week from now. So we're going to share the videos through our YouTube channel of the next lab, and these slides on Dropbox. But all the information are going to be provided and sent out via our LinkedIn webpage. So thank you all once more. Thank you for all the attendance. Thank you for all the speakers. And well, for us, see you tomorrow for the next Research Line Fair event for the next camp guys that are going to end phase 1 and guys and gals that are going to end phase 1 and going to start phase 2. So thank you all once more, and see you in 6 months from now on July the 26th and 25 for the new edition of the next Research Line Fair event. See you all, bye, and thank you.